In this video, I will be discussing about permutation. This is another rule on counting with the number of arrangements with regards to the order of the items. And this counting rule are the concern of permutations. So here, order matters. We are concerned with the order. So what is permutation here? Permutation is an arrangement of all or part of the set of objects. And this illustrates that, for example, 725 is a different arrangement from 752 because of the different order of the elements or digits in the two numbers. Similarly, if we have AB, this is also different arrangement from BA because order here matters. So what is permutation? Permutation is the statistical term for arrangement. So we are after here with the arrangement of the objects in the set. Hence, we can use arrangement instead of the word permutation. So roughly speaking, we can use these two words interchangeably here, the permutation and arrangement. So instead of using permutation, we can use arrangement here because we are after with the arrangement of objects in the set. So allow me to give you the first theorem here. The number of arrangements of n different distinct objects is n factorial. And then the number of permutations of n distinct objects taken r at the time is npr. npr means the permutation of n taken r at a time, which is equal to n factorial divided by n minus r factorial. And also, the number of arrangements of n distinct objects arranged in a circle is given by n minus 1 quantity factorial. And then the number of arrangements of n distinct objects arranged around a ring is n minus 1 factorial divided by 2. And lastly, the number of distinct arrangements of n elements wherein n is the sum of n sub 1 plus n sub 2 plus n sub 3 and so on until n sub k, of which n sub 1 are alike and n sub 2 are also alike, and so on and so forth, then the total distinct arrangements is equal to n factorial divided by n sub 1 factorial times n sub 2 factorial times n sub 3 factorial, and so on and so forth to n sub k factorial. Now, let's have our illustrative examples to illustrate those permutation theorems. In how many ways we can arrange the letters of the word love? Now, listing them could be a tedious process because if you list down all possible arrangements, you can have L-O-V-E or L-V-O-E, or it could be L-E-O-V, or it could be L-E-V-O, listing down all of those possible arrangements of these letters could be a tedious process. So I can use here our first theorem, which is the 4 factorial, because in the first theorem, we are arranging all the objects in the set. And if you arrange these objects in the set, that can be counted as 4 factorial. And what is 4 factorial? That is 24, because that's 1 times 2 times 3 times 4. So there are 24 ways you can arrange the letters of the word love. But you can still use our fundamental principle of counting by just creating 4 boxes here. And these 4 boxes represents the 4 positions of the letters of the word love, in which the first position you can have 4 choices from the 4 letters of the word love. So you can place L in the first position, or O, or V, or E there. But in the second position, I cannot place all of the 4. But I am left with 3 choices now because one of the letters in the word love is being used in the first position. And so with the third position, I am left with 2 choices because 2 of the 4 letters of the word love were already chosen in the first and the second position, as well as in the last position, that I am left with 1 choice here. So multiplying these numbers, I will get a product of 24. So you can see that our answers are just the same. So our first solution is using the permutation theorem because we are arranging all the letters in the word love, but we can still use our fundamental principle of counting by multiplying all possible occurrences. Number 2, in how many ways can 4 boys and 4 girls be seated in a row of 8 chairs if they may sit anywhere? So here, we can use still our first theorem because we are arranging all of them regardless of gender. So that is 8 factorial. And we know that 8 factorial is the product from 1 to 8. And the answer is 40,320 ways. In other words, there are 40,320 ways we can arrange these 8 students in a row of 8 chairs. But we can still use our fundamental principle of counting. We will be creating 8 boxes here to represent the 8 chairs. So in the first chair, any of the 8 persons can sit in the first chair. So we have 8 choices here. In the second chair, if one of them has seated already in the first chair, I am left with 7 students in the second chair. And in the third chair, 6, the fourth chair, 5, and so on and so forth. And then multiplying these numbers, we get 40,320. And you can see that our answers using the 2 methods are just equivalent. Now let's proceed to our third problem. How many different permutations or arrangements are possible with the letters of the word love taken 2 at a time? So in this problem, we are taking 2 letters at a time from the word love. So it's a different problem from the first problem because in the first problem, we are arranging all the letters at a time, meaning you are taking all of them when you arrange the letters. But here in the third problem, we are taking only 2 letters at a time. So we can have LO or LV or LE or OL or VL or EL and so on and so forth. But using our theorem, this is the permutation of 4 letters taken 2 at a time. And we know that the formula of this is 4 factorial divided by 4 minus 2 factorial. Since our n is 4 and our r is 2 here. So we know that this is 4 factorial divided by 2 factorial. And 4 factorial is equal to 4 times 3 times 2 factorial because 2 factorial is 2 times 1. And why is it that I'm doing that? So that I can cancel it from the denominator. So canceling those 2, we are left with the product of 4 and 3. And our answer is 12 permutations or 12 arrangements. If you arrange 2 letters at a time from the word love, but we can still use our fundamental principle of counting here by creating 2 boxes. The first box is for the first letter and the second box for the second letter. And out of the 4 letters of the word love, I can choose any of them. So that's why we have 4 choices in the first position. But in the second position, I am left with 3 choices now because one of the letter in the word love is already being placed in the first position. So we have 3 here, and multiplying these numbers, we get the product of 12. And you can see that our answers are just the same here. Now let's proceed to our fourth example. In how many ways can 4 boys and 3 girls can be seated in a row of 5 chairs? Now here we can still use our second theorem, that this is the permutation of 7 students from the 4 boys and 3 girls, and then take 5 students at a time, irregardless of their gender. So this is 7 factorial divided by 7 minus 5 quantity factorial. And we know that 7 minus 5 factorial is 2 factorial. So this is 7 factorial divided by 2 factorial. And 7 factorial divided by 2 factorial is equal to 2,520 ways. But we can still use our fundamental principle of counting by creating 5 boxes here. And the 5 boxes represents the 5 chairs because we will be sitting 5 students at a time. So out of the 7 students, we can have any of the 7 students for the first chair. And in the second chair, I am left with 6 students because one of them has seated already in the first chair. And in the third chair, I am left with 5 choices because 2 of the 7 students has seated already in the first 2 chairs, and so on and so forth. And then multiplying all these numbers, we get 2,520. So you can see that our answers are just the same using the permutation theorem or using the fundamental principle of counting. Now let's proceed to our fifth problem here. In how many ways can 4 boys and 4 girls be seated in a row if the boys and the girls must alternate? Now here, because gender is being considered, I will be arranging first the boys and to arrange alternately. So one case is putting the boy first and then followed by a girl, boy, and a girl, boy, and a girl, and a boy, and a girl. So that's arranging the 4 boys and 4 girls alternately here. But you can also place the girl in the first position. So girl first and then followed by the boy, then the girl, the boy, the girl, the boy, the girl, and then the last boy. So therefore, I can count the number of ways by arranging first the boys. So all the boys, I can arrange that one by using the permutation of 4 taken 4 at a time. And also the girls is the permutation of 4 taken 4. And why is it that I am multiplying it by 2? Because there are 2 cases here. 2 ways I can arrange these 4 boys and 4 girls. One, when the boy is in the first position, and the other case is when the girl is in the first position and then followed by a boy. So therefore, if you compute for the permutation of 4 taken 4 at a time, that is 4 factorial. And also for the girls. So we know that 4 factorial is 24. So we have 2 times 24 times 24. So we have a product of 1,152. But we can still use our fundamental principle of counting by creating 8 boxes here. And then by arranging first the boys. So we have 4 in the first position for the boy, and then the second position of the boy, and that's 3 because I am left with 3 choices out of the 4 boys, and then 2, and then 1. So 4 times 3 times 2 times 1 is the total arrangements of all the boys when a boy is in the first position. And also for the girls, we can arrange them by putting 4 times 3 times 2 times 1. But because there are two cases here, since a girl can be arranged first, then I need to multiply it by 2. So multiplying these numbers, I will get the same answer here. So using our fundamental principle of counting, comparing it to the permutation theorems, we get the same answer. Now let's proceed to our sixth problem here. In how many ways can 4 people be seated at a round table? Now, solving this one using our permutation theorem, this is 4 minus 1 factorial, since there are 4 people arranged at a round table. So we have 3 factorial, and 3 factorial is equal to 6 here. So there are 6 ways we can arrange 4 people seated at a round table. Or you can use our fundamental principle of counting. So here I will draw a round table wherein I can place the 4 chairs around to it. Now I can place the first person as a reference person because this is a circular arrangement. And why is it that there is a fixed person? Because this is a different arrangement from the linear arrangement that we discussed, since we know who is the first person. So here I will be using one of the 4 people to be a fixed person, and then I will rearrange the remaining 3 in the 3 chairs. So in the next chair I can place any of the 3 remaining people, and also 2 on the next chair, and then I am left with 1 person to sit in the last chair. So multiplying these numbers, we get 3 times 2 times 1 here. So the product is 6 ways. Then therefore there are 6 ways of arranging these 4 people at a round table. Now let's proceed to our example number 7. In how many ways can 5 different trees be planted in a circle? Now, using our permutation theorem, this is 5 minus 1 factorial. And 5 minus 1 is 4 here. So 4 factorial, we know that's 24. Then therefore, there are 24 ways you can plant these 5 different trees in a circular pattern. But we can still use our fundamental principle of counting by drawing a circle here and then placing the 5 different spots in a circular pattern. So in the first spot, I can place any of the 5 trees as a fixed position, and then the remaining trees will be arranged in the 4 spots. So in the first spot, I can choose any of the 4 remaining trees, then 3, and then 2, and then 1. So multiplying those numbers, we get 24. And you can see that our answers are just the same. So let's proceed to our 8th example here. In how many ways can 4 keys be arranged in a circular ring of a key holder? Now, this problem is still a circular permutation, but this is around a ring, and we know that a ring can be flipped here. So solving using our theorems, we have 4 minus 1 factorial divided by 2. So 4 minus 1, that's 3. And 3 factorial divided by 2 is 3 here. So therefore, there are 3 ways of arranging the 4 keys around a circular ring of a key holder. But we can still use our fundamental principle of counting here. And drawing the circular ring of a key holder, I can draw also the 4 position of the keys and use the first key as the fixed position, and the remaining 3 keys will be placed in the 3 spots there. So 3, and then 2, and then 1 there. But because this is a circular ring, which is different from sitting in a round table, we can flip this circular ring. Now, comparing this one from the first problem, we cannot flip the round table and sit in a flipped table and get their arrangement. So here, we divide it by 2 because we can flip the ring. So 3 times 2 times 1 divided by 2, we know that is 3. So you see that our answers are just the same when using the fundamental principle of counting or using the theorem. Number 9. How many distinct permutations can be formed from the letters of the word statistics? So here we will be using the last theorem, the fifth theorem. So we know that there are letters that are identical here. We have 3 S's in the word statistics and 3 T's in this word and 2 I's in the word statistics. So using the theorem, that is 10 factorial divided by 3 factorial times 3 factorial times 2 factorial, because 10 factorial in the numerator is arranging all of the 10 letters of the word statistics, but 3 of them, which is S, are identical, so we need to remove them. Because when you rearrange the 3 identical letters, you cannot notice that these are rearranged. So we need to divide it in order to remove those arrangements. And then also for T, we need to divide it by 3 factorial because there are 3 T's in the word statistics. So we need to remove the 3 factorial as the arrangements of the letter T, which are identical, and so with the I, which is 2 factorial. So solving this one, the 10 factorial can be expressed as 10 times 9 times 8 times 7 times 6 times 5 times 4, and then times 3 to 1. But the product from 3 to 1 is 3 factorial, so that we can cancel this one from the denominator. So therefore, our product is 50,400 permutations. So there are 50,400 distinct arrangements we can form from the letters of the word statistics. But we can still use our fundamental principle of counting here. So creating the 10 boxes for the 10 letters, we can place any of the 10 letters in the first position. So we can place there 10 and then 9 in the second position, because you cannot place the one that is being placed in the first position. And then 8, 7, 6, 5, 4, 3, 2, 1. This is the total arrangements of the 10 letters. But there are letters that are identical there that were counted in this product. So therefore, we must have to remove those arrangements. So for the letter S, which are 3 of them, we need to divide it by 3 times 2 times 1, which represents the arrangements of the 3 identical letters, which are S's, and also there are 3 identical T's here. So we need to divide again by 3 times 2 times 1. And also for the 2 I's, we need to divide 2 times 1. So performing the simple arithmetic, we know that the result is still 50,400. And you can see that both of our answers are just the same. Now let's proceed to our 10th problem. Morse code uses dots and dashes arranged in a row. So in a Morse code, we have 3 dots and 4 dashes. How many symbols can be formed from using 3 dots and 4 dashes? So in this case, we know that our n is 7 because there are 3 dots and 4 dashes, because we have 7 characters here, the 3 dots and 4 dashes. So we have 7 factorial for the 7 characters divided by the 3 dots that are identical in the 7 characters. and also 4 factorial for the 4 dashes that are identical. So expressing 7 factorial as 7 times 6 times 5 times 4 factorial, and also 3 factorial in the denominator, which is 3 times 2 times 1, and multiplied by 4 factorial, we can cancel the 4 factorials in both numerator and denominator. So we have 35 as our answer. But we can still use our fundamental principle of counting by creating the 7 boxes here, because there are 7 characters that we need to arrange. So I can have 7 in the first position, and then 6, 5, 4, 3, 2, 1. And the product of this is the arrangements of the 3 dots and 4 dashes. But we know that the 3 dots there are identical, so we need to remove the arrangements of the 3 dots which are non-noticeable for us because they are identical. So we need to divide this by 3 times 2 times 1. And then also we need to divide it by 4 factorial for the 4 dashes that we rearrange but cannot be noticed in the arrangement because they are identical. So performing simple arithmetic, we can cancel this 4 times 3 times 2 times 1, and so with the 6 in the numerator, which can be cancelled by the 3 times 2 in the denominator. So we have 7 times 5 divided by 1. Then therefore our answer is 35, which is equal to our answer using the permutation. So at this point, let us discuss about ordered samples. So what are ordered samples? Actually, there are 2 types of sampling when you want to get samples from a population in succession. Drawing a ball from an urn containing n balls for several times is what we mean by ordered sampling. When we choose one ball after another from the urn, say r times, we call the choice an ordered sample of size r. So here, it's like drawing one ball at a time from the urn until you will reach r balls. But actually, there are 2 cases that we need to consider here: sampling with replacement and sampling without replacement. So what is this sampling with replacement? Here, the ball is replaced in the urn before the next ball is chosen. So in symbols, the number of different ordered samples with replacement of size r is just the product of the size of the balls from an urn. So this is n times n times n until the last n, which is the rth n. So you will be multiplying r times of n. And if you're going to multiply this one, this is equal to n to the power r. However, sampling without replacement happens when the ball is not replaced in the urn before the next ball is chosen. Thus, there are no repetitions in the ordered sample, which means that when that ball was drawn in the previous draw, there is no chance that this will be drawn in the succeeding draws, because you will not replace that ball to the urn when this ball is being drawn already. So in symbols, the number of different ordered samples without replacement of size r is NPR. In other words, it's the permutation of n taken r at a time. So this is equal to n factorial divided by n minus r factorial. Now, let us have illustrative examples to illustrate the concept we have presented. And in this example, we are asked, in how many ways can one choose 3 cards in succession from a pack of 52 cards? Letter A, with replacement. Letter B, without replacement. So just imagine a standard deck of playing cards wherein you have 4 suits. You have hearts, you have diamonds, you have spades, you have clubs there. And there are 13 in each suit. And since there are 4 suits, 4 times 13 is equal to 52. So for number 1, you want to draw 3 cards in succession from that standard deck of 52 cards. Then you will be creating 3 boxes to represent the 3 cards that you want to draw from the standard deck of cards. So during the first draw, you have 52 choices for your first card. But remember, after you draw the first card, you will return this card to the standard deck of cards and shuffle again the whole cards. And then you will choose your second card. So for your second draw, you can have 52 choices for your second card because you still have 52 cards there. And after the second draw, you will return that card to the standard deck of cards and shuffle again before you draw the third card. And then again, during the third draw, you can have 52 choices because you still have 52 cards there. And then multiplying these numbers, you will get 140,608 different ordered samples of size 3 that you can get from the standard deck of cards when you draw 3 cards one at a time with replacement from the standard of 52 cards. But here, you can use the formula that we have presented in the previous slide, that you can raise this 52 to the exponent of 3 because this is sampling with replacement. And why is it you have an exponent of 3? Because your sample size is 3. So therefore 52 cubed, and 52 cubed is still equal to 140,608 different ordered samples of size 3. And you noticed that we've got the same answer with our solution using the fundamental principle of counting. Now let's proceed to the solution for letter B question. How many ways you can choose your 3 cards in succession from a 52 deck of cards without replacement at this time? So because you are drawing 3 cards in succession, you will be creating 3 boxes here. And the first box represents the result of your first card during the first draw. And in the first draw, you can have 52 choices because there are 52 cards there. But in the second draw, you can have only 51 choices because you will not return the card to the standard deck of cards when that card was chosen during the first draw. And also, for the third card, there will be only 50 choices because 2 out of 52 cards were already chosen during the first 2 draws. And multiplying these numbers, you can have 132,600 different ordered samples of size 3. So here, we are using our fundamental principle of counting, but of course, we can still use the formula that we have presented in the previous slide, that if this is an ordered sample in succession without replacement, then we can use our permutation formula, that this is the permutation of 52 taken 3 at a time. And we know that using the permutation formula, this is equal to 52 factorial divided by 52 minus 3 quantity factorial. So 52 factorial divided by 49 factorial, because 52 minus 3, the difference is 49. And 52 factorial can be expressed as 52 times 51 times 50 times 49 up to the last whole number, which is 1. And that product from 49 to 1 is represented by 49 factorial. And why is it that I'm doing that? So that I can cancel this 49 factorial with my 49 factorial in the denominator. So I am left with these factors of 52, 51, and 50. And we know that this is equal to 132,600. So there are 132,600 different ordered samples of size 3 that you can obtain when you draw 3 cards in succession from a standard deck of cards without replacement. Now let's proceed to our next example here. A car dealer has 4 types of cars from which 3 customers will pick one. How many different sales can the dealer make? Now, in this problem, let us use our common sense that this is an ordered sample with replacement because the car company has more than 1 car of each type. So you can make here 3 boxes, and the 3 boxes represents the 3 choices of the 3 customers here, in which the first customer can choose any of the 4 types, but the second customer can still have the 4 choices because common sense would tell you that that car company has more than 1 car of each type. And also, the third customer can choose any of the 4 types there available. So multiplying these numbers, you will have 64 different sales. Or you can use the formula that 4 is raised to the exponent of 3 because this is an ordered sample with replacement, that each customer can choose any of the 4 types available from the car sales. So we have 64 different sales here. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.